All right, complex number and a theorem to go over. So we've plotted numbers on the polar axis. We've plotted them on a rectangular coordinate grid. Now we're going to plot them on the complex number axis. So it looks very similar to rectangular coordinates, with the exception of the y-axis is now your imaginary axis. So you have a real axis and you have an imaginary axis, but they work the same. Right positive, left negative, up positive, down negative. All right, first thing, absolute value of a complex number. So when we have the complex number a plus bi, the absolute value is the length of the hypotenuse. So example 1, find the absolute value of each complex number below. So we're given z equals 2 minus 3i. So the absolute value of z is going to be the sum of the squares of the legs square rooted. So a is 2 plus b is negative 3, and then that sum is square rooted. So z equals 2 squared, 4 plus negative 3 squared, 9, square root of 13, which does not reduce, so there's nothing we can do there. All right, b, negative 7 plus 9i. So the absolute value of z is negative 7 squared plus 9 squared under a square root. So we get 49 plus 81 under a square root. So the absolute value of z is 130, square root of 130, which if we try to reduce, it does not reduce, so we would leave it as is. All right, polar form of a complex number. So we can write a complex number in polar form. It's the radius times the quantity cosine of theta plus I sine of theta. So remember, cosine x, sine y. So same concept when we go to imaginary numbers. The I is attached to what we would refer to as the y, or the vertical distance. Same ratios as before. Cosine of theta is a over r, sine of theta b over r, and then tangent is going to be b over a. All right, so writing each of the following in their other form. So going from polar to rectangular and then vice versa. So this one is complex. This is in complex form. We want to go to polar form. So we need to identify A and we need to identify B. So here A is negative 1, B is negative square root of 3. So we need to find R. R equals the sum of the squares of A and B square rooted. So negative 1 squared plus negative square root 3 squared under a square root. So R is going to be 1 plus 3, 4, square root of 4, 2. So we have our radius. For our angle, remember, when you're dealing with angles, you've got to make sure you're in the correct quadrant. So before I go do my angle, I want to make sure I know what this looks like. So I'm going to go plot my polar number just to make sure I do put the angle in the correct quadrant. We do not want to put it in the wrong quadrant. So I don't need a large graph, I just need a little baby graph. All right, so the polar number, negative 1 goes left. Square root of 3i goes down, so that's telling me we're in quadrant 3. I don't necessarily need the exact location, but I do need the quadrant number. So we are in quadrant 3. All right, so the angle. Tangent of theta is the ratio of b over a, y over x. So imaginary over horizontal, because the imaginary is taking the place of the y-axis. So negative square root of 3 over negative 1. So that means tangent of theta, double negative makes positive. And I'm going to leave it there for now. Actually, we can drop that. and I'm going to put my 2's back. So remember, it is helpful a lot of times in figuring out these ratios to put those that 2 back in those denominators, because remember that does divide out. Just makes it easier to find that angle. So I know y is the long side, x is the short side, which means I'm looking at a pi third. And in quadrant 3, that would be the 4 pi third angle. So theta is 4 pi over 3. All right, so now that we have our theta and our r, we can write the polar form. So polar form is z equals r2 times the quantity cosine theta, which is 4 pi third, plus I sine theta sine 4 pi third. Let me scoot my angle up so it's not in the way of the answer. Okay. Reversing it. So now we're given the polar form, so we're going to go backwards to the rectangular form. All right, so first thing we need to do, we need to identify, it's helpful to identify the radius r and the angle theta. So our radius here is 2. Our angle theta is 60 degrees. We need to find a and b. So a is equal to r times the cosine of theta. So a is going to be 2 times the cosine of 60. The cosine of 60 is 1/2. So we've got 2 times 1/2, which is just 1. So I'm just going to go ahead and simplify it down to 1. We need b. B is r sine theta. So b equals 2 times the sine of 60. So the sine of 60 is the square root of 3 over 2. Square root of 3 over 2 times 2 is the square root of 3. So we have our A, we have our B, so our number is A1 plus B root 3I. All right, product of two complex numbers, so we can multiply and divide complex numbers just like we do regular numbers. So what it winds up doing is you take your 2 radii, you multiply your radii, transitions to add your angles. Multiply your radii, add your angles. All right, first example, find the product of the complex numbers z sub 1 equals 6 times the quantity cosine 40 theta plus I sine 40 degrees, not theta, and z2 5 times the quantity cosine 20 degrees plus I sine 20 degrees. So product z1 times z2 equals the product of the radii, so 6 times my second radii, 5, and then cosine of the sum of the angles, so 40 degrees plus 20 degrees, plus I times the sine of the sum of the angles, 40 degrees plus 20 degrees. Multiply the radii, add the angles. So that gives us 30 times the quantity cosine 60 degrees plus I sine 60 degrees. So we don't want to keep going because it says to leave our answer in polar form. So we want to leave it just like this. All right. Quotient, so we've multiplied 2 complex numbers. We can also divide 2 complex numbers. So division translates in the same way as the multiplication. Multiplication was multiply, add. So division is divide, subtract. All right, so z1 over z2, I think is what we're looking for. Find the quotient. Yeah, we're just going to do z1 over z2. I should have labeled that. So we take our radii, we divide them, so 50 divided by 5 times the quantity cosine first minus second, so 4 pi third minus pi third plus I sine first minus second. 4 pi third minus pi third. So that gives us, we do the little math here, 50 divided by 5, 10. Cosine 4 minus 1, 3. 3 pi over 3 is pi, plus I sine pi. All right, De Moivre's theorem. So what this theorem allows us to do is find powers of complex numbers. So like if z is your complex number, find z to the second power or z to the third power or 50th for fun. All right, so example 4, find if z equals 2 times the quantity cosine 30 plus I sine 30, find z to the 5th. All right, so we're going to plug into De Moivre's theorem. So z to the 5th equals, it is the radius to that power, so our radii is 2. So 2 to the 5th times the quantity cosine of n theta, so that's going to be 5 times 30 degrees, plus I sine of that same product, 5 times 30 degrees. So that gives us 2 to the 5th, 32, times cosine of 150 plus I sine 150. All right, so if we read the directions, give your answer in polar, done, and rectangular form. So this would be our polar answer. So I'm just going to label it over here to the side, polar. So rectangular form means we need to go and simplify this thing. I was going to box this in. Get our polar answer. All right, rectangular form means we need to go all the way down to the values of these. So cosine of 150, I'm not very good with my degree angles. 150 is equivalent to 5 pi 6. So cosine of 5 pi 6 is negative square root of 3 over 2. Plus I times sine, so the y value of 150, the y value of 5 pi 6, 1/2, because it's in quadrant 2, so it's positive. And then we can distribute our 32. So 32 divided by 2, 16, so negative 16 square root of 3 plus 32 divided by 2, 16i. So this would be our rectangular. So 2 answers. So again, read very carefully. You don't want to get it wrong because you answered in the wrong format. If it says polar form, stop once they're plugged in and the angle's simplified. If it says rectangular form, go all the way to the end, a plus bi form. Last thing we're going to look at is called De Moivre's theorem for finding complex roots. So there's a double equal sign there. There should not be. A little scribble will get rid of it. So changing the letter just for fun. So that's omega. It looks like a scripted W. So W is a complex, or omega is a complex number. Then as long as that complex number does not equal 0, it has indistinct complex roots given by the formula here. So notice the theta plus 2 pi k over n, where we just rotate through the different integer values beginning at 0 and going up to n minus 1. All right, so finding the complex roots. So we're going to find the complex fourth roots of the complex number 16 times the quantity cosine 60 degrees plus I sine 60 degrees. It says leave the answer in degrees. All right, so first we need to know is what roots. We want fourth roots, so that means n equals 4. So as far as rotating through, we're going to rotate through plugging in different values of k, going from k equals 0, 1, 2, and 3. So I'm going to go ahead and write that out because I don't want to go too far. So k, we're going to plug in k equals 0, 1, 2, and we stop at 1 below n, so 3. So we got to plug in all of these. So first thing I'm going to do is get my formula set up. So z sub k is going to be the fourth root, because we're doing the nth root, of r, and r is 16, times the quantity. You know what, I'm going to use a bracket here instead. Cosine, and it says degrees, so we're going to use the 360 format. Theta plus, whoops, I forgot to plug in theta. 60 plus 360k over 4. So in the formula above, let me go back to it here. In the formula above here in your notes, I put 2 pi, but there is that note, if we're in degrees, replace 2 pi with 360. And then plus I times the sine of that same 60 degrees plus 360 degrees times k over 4. All right, so nitpicky in the calculation, but this is what we're going to be going through. All right, so we're doing for k equals 0, k equals 1, 2, and 3. So a whole lot of plugging in here. All right, so z sub 0. 4 through to 16 is 2. I'm going to go ahead and simplify that to 2. Plugging in 0 for k is going to give us cosine of 360 times 0 is 0. So we've just got the 60 divided by 4, which is 15. Plus I, the angles are going to come out the same, sine of 15. And it says leave it in degrees. Well, obviously we have to. We can't do cosine of 15. I mean, we could use a half-angled identity, but we got enough work. All right, z sub 1 is going to be 2 times the quantity. So now what we're going to do is we're going to be plugging in our formula above. We're going to be plugging in 1 for k. So when we plug in 1 for k, that gives us 360 times 1, so 360, plus the angle 60 divided by 4, 105. So I'm just going to go ahead and simplify the angles all the way down. And the nice thing is the angles are going to be the same, 105. And now plugging in z equals 2. Not z equals 2, k equals 2. So cosine, checking our angles. So 2 for k gives us 2 times 360 plus 60 divided by 4. So 195. And then finally, Z3, remember to stop at 1 less. So Z3, 2 times the quantity, now plugging in way back up here, plugging in 3, so 3 times 360 plus 60 divided by 4 gives us 285. And that's it. Okay. So same process. If it gave you the initial angle in radians, it's going to have you leave your answer in radian form. So instead of like it saying cosine of 15, it would say like cosine pi 12 plus I sine pi 12.